Hello my good friends, Derek Deschamps here for Internetworking Influencers, your source for free Cisco certification training for network engineers. Welcome to day 5 of our free CCNA 100-105 ICND1 training course. The Internetworking Influencers CCNA 100-105 ICND1 training course is comprised of 13 videos, each focusing directly on a set of specific items on Cisco's official exam topic list. Today's episode will cover item 1.11, identify the appropriate IPv6 addressing scheme to satisfy addressing requirements in a LAN-WAN environment. Item 1.12, configure, verify, and troubleshoot IPv6 addressing. Item 1.13, configure and verify IPv6 stateless address auto-configuration. And item 1.14, compare and contrast IPv6 address types, including global unicast, unique local, link local, multicast, modified EUI64, auto-configuration, and anycast. If you would like to have a look at Cisco's official exam topic list, I've included a link to it in the show notes. As a reminder, today's video has a set of free practice questions that are available on our website at internetworkinginfluencers.com that will help you brush up on the topics you learned today. The questions are a true representation of the types of questions you'll face on the actual exam, so be sure to check those out once we're done. Today we'll start things off by looking at IPv6 addressing. IPv6 is the successor to IPv4 and was developed due to a shortage of IPv4 addresses. IPv6 provides a significantly larger address pool than IPv4. Devices can run both IPv4 and IPv6 at the same time, which is referred to as dual stack. An IPv6 address is a 128-bit number that can be used to identify each network interface on a network. The 128 bits is divided into 8 groups of 16 bits. Each 16-bit group is represented by 4 hexadecimal digits and separated by a colon. This means each hexadecimal digit represents 4 bits. This is important to remember when converting IPv6 addresses from hexadecimal to binary. We need to remember to express each hexadecimal digit as 4 bits. For example, the hexadecimal digit 2 would need to be expressed as 0010 in binary. For those of you that aren't familiar with hexadecimal, it is a base 16 numbering system that uses 16 digits, the numbers 0 through 9, and the letters A through F. Converting hexadecimal to decimal is relatively simple. The numbers 0 through 9 and the letters A through F in hexadecimal correspond to the numbers 0 through 15 in decimal. This means when converting hexadecimal to binary, we can simply use the decimal equivalent and follow the same decimal to binary conversion techniques we learned about in the last episode. Since IPv6 addresses are quite long, there are a few methods used to simplify how they are represented in hexadecimal format. The leading zeros in each of the 8 groups can be dropped, as long as a minimum of 1 digit remains. For example, the leading zeros in the 3rd, 4th, 5th, and 7th group of this IPv6 address can be dropped. Any 2 or more consecutive groups containing all zeros can be dropped and replaced with 2 colons. For example, the 4th and 5th group of this IPv6 address can be replaced with 2 colons. It is also important to note that you can only do this once. So if more than one sequence of consecutive groups containing all zeros existed, you would apply this method to the largest consecutive group. If they happen to be equal-sized consecutive groups, you would apply this method to the leftmost group. There are several types of IPv6 addresses that you need to be familiar with for the exam. A global unicast address is the IPv6 equivalent to a public IPv4 address. Global unicast addresses are globally unique and used by hosts and devices that need to be accessed from the Internet. Global unicast address allocation is managed by the Internet Assigned Numbers Authority. Address assignments are currently limited to the range 2000::/3. A global unicast address is comprised of three parts. The global routing prefix is the portion of the address that is assigned by the Internet Assigned Numbers Authority and is used to identify an individual site. The subnet bits are used to number individual subnets in the same way they are used in IPv4. The bits that comprise the interface ID are used to identify individual host addresses in the same way that host address bits are used in IPv4. The global routing prefix combined with the subnet bits make up the subnet prefix, which is used to identify individual subnets in the same way as a subnet ID in IPv4. In IPv4, a subnet mask is used to differentiate between the bits that are used to identify the network and the bits that are used to identify hosts. The same concept holds true in IPv6. Only a subnet mask is referred to as the prefix length. For example, a prefix length of 64 indicates that the first 64 bits of the IPv6 address are used to identify the network, leaving the last 64 bits to identify hosts. Subnetting is also performed the same way as with IPv4, only now due to the large number of bits in an IPv6 address, everyone tends to use a prefix length of 64 to simply divide the address in half. So for example, if a company was assigned a 48-bit global routing prefix, then 16 bits would typically be used for subnet bits to make a prefix length of 64. 64 bits would then be used as interface ID bits. A unique local address is the IPv6 equivalent to a private IPv4 address. Unique local addresses are reserved for private networks and are not routable on the Internet. Unique local addresses are used for communication within an internal network. Unique local addresses begin with FD as the first two hexadecimal digits, taking up 8 bits. The next 40 bits make up the global ID, which is chosen randomly by the administrator. The next 16 bits are used as subnet bits, leaving 64 bits to be used as interface ID bits. A link local address is an additional address assigned to each IPv6 interface. A link local address can only be used for communication within a single subnet and is not routable by routers. A link local address is generated automatically if not explicitly configured. A link local address is used for neighbor discovery, automatic address configuration, and as the next hop address for IPv6 routes. The first 64 bits of a link local address always begin with FE80 as the first 4 hexadecimal digits, followed by 3 groups of all zeros. The remaining 64 bits make up the interface ID, which is often generated automatically, however, can be configured manually. On a Cisco device, if an IPv6 interface does not have a link local address manually configured, the link local address will be configured automatically, with the interface ID generated using modified EUI64. Modified EUI64 is a method used to create a 64-bit interface ID for an IPv6 address. The 64-bit interface ID is created by inserting the hexadecimal digits FFFE into the middle of the interface's 48-bit MAC address, and then inverting the 7th most significant bit. For example, let's look at an interface with a MAC address of 001F 331D 68E2. To get the modified EUI64 interface ID for this interface, we first insert the hexadecimal digits FFFE into the middle of the interface's MAC address, which gives us 001F33FFFE 1D68E2. Secondly, we invert the 7th most significant bit. To calculate this, we take the first 2 hexadecimal digits starting from the left, which represent bits 1 to 8, and convert them to binary. We then invert the 7th most significant bit, and convert the result back to hexadecimal. In this case, the first 2 hexadecimal digits starting from the left are 00. Converting this to binary gives us 00000000. Inverting the 7th most significant bit gives us 00000010. Converting the result back to hexadecimal gives us 02. This means our modified EUI64 interface ID is 021F33FFFE 1D68E2. An IPv6 multicast address functions in a similar manner to an IPv4 multicast address, in that packets sent to a multicast address will be delivered to all hosts in that multicast group. An IPv6 multicast address begins with the hexadecimal digits FF. A link local multicast address is a multicast address that is not routable by routers, and therefore can only be used for communication within a single subnet. A link local multicast address begins with the hexadecimal digits FF02. Examples of link local multicast IP addresses include FF02:1, which is used to send packets to all nodes on a subnet. FF02:2, which is used to send packets to all routers on a subnet. FF02:5, which is used to send packets to all OSPF routers on a subnet. FF02:9, which is used to send packets to all RIP-NG routers on a subnet. And FF02:A, which is used to send packets to all EIGRPv6 routers on a subnet. Solicited-node multicast addresses are multicast addresses that are automatically generated for each IPv6 unicast address on an interface. Solicited-node multicast addresses are not routable by routers and are used for neighbor solicitation. A solicited-node multicast address begins with the hexadecimal digits FF02 in the first group, all zeros in the second, third, fourth, and fifth group, followed by 0001 in the sixth group, and the seventh group always begins with FF. The last 6 hexadecimal digits contain the last 6 digits of the IPv6 unicast address assigned to that interface. It is also important to note that since only the last 6 digits of the unicast address are used, some hosts on the same subnet may share the same solicited node multicast address. An IPv6 anycast address is an address that is assigned to more than one interface, usually on different hosts. Packets sent to an anycast address are routed to the nearest interface with that address. Anycast addresses are allocated from the standard unicast address space. For example, multiple DNS servers may use the same anycast address. When a host sends a DNS query to the anycast address, their request is routed to the nearest DNS server configured with that address. The next topic we will cover today is IPv6 stateless address auto-configuration. IPv6 stateless address auto-configuration, or SLAAC, allows hosts to automatically configure their own IPv6 address. When IPv6 stateless address auto-configuration is used, the prefix portion of the IPv6 address is learned from a local router using the Neighbor Discovery Protocol, or NDP. The interface ID is generated using modified EUI64. As I mentioned, the prefix portion of a SLAAC address is obtained by using the Neighbor Discovery Protocol, or more specifically, through the use of router solicitation messages and router advertisements. A router solicitation, or RS message, is a message sent to the multicast address FF02::2 that asks all routers on the local segment to send a router advertisement. A router advertisement, or RA message, is a message sent by a router that contains the router's IPv6 address, prefix information, and preference to act as a default gateway. Router advertisements are sent periodically or as a response to a router solicitation. Neighbor Discovery Protocol also consists of 2 other types of messages. A neighbor solicitation, or NS message, is a message sent to the solicited node multicast address of an IPv6 address that asks the recipient to reply back with its MAC address. A neighbor solicitation message is the IPv6 equivalent to an IPv4 ARP request. A neighbor solicitation message is also used for duplicate address detection, or DAD, to determine if an IPv6 address is in use. A neighbor advertisement, or NA message, is a response to a neighbor solicitation message containing the sender's MAC address. A neighbor advertisement is the IPv6 equivalent to an IP version 4 ARP reply. With IP version 6 DHCP, or DHCPv6, a stateful DHCPv6 server is responsible for assigning the unicast address, prefix length, as well as parameters such as DNS servers, domain name, or NTP servers, while the neighbor discovery protocol provides the default router information. With stateless DHCPv6, a host can use stateless address auto-configuration to determine its own unicast address. The host can also use neighbor discovery protocol to determine the prefix, prefix length, and default router information. This means the only information the stateless DHCPv6 server needs to provide is information that does not need to be updated for each client, such as DNS servers, domain name, or NTP servers. And lastly, let's take a look at the IP version 6 commands you should be familiar with for the exam. The IP version 6 unicast-routing command is a global configuration command used to enable IP version 6 unicast routing on a router. The IP version 6 enable command is used to enable the IP version 6 process on an interface and automatically generate a link local address. The IP version 6 enable command is not required if any IP version 6 address is explicitly configured. The IP version 6 address command is used to manually configure an IP version 6 address on an interface. The IP version 6 address link local command is used to manually configure an IP version 6 link local address on an interface. The IP version 6 address EUI64 command is used to configure an IP version 6 address on an interface and use modified EUI64 to generate the interface ID. The IP version 6 address anycast command is used to configure an IP version 6 anycast address on an interface. The IP version 6 address autoconfig command is used to configure an IP version 6 address on an interface using stateless address autoconfiguration. The IP version 6 address DHCP command is used to configure an interface to acquire an IP version 6 address from a DHCPv6 server. The show IP version 6 interface brief command is used to verify the IP version 6 address information for all interfaces, while the show IP version 6 interface command is used to verify the IP version 6 address, prefix, prefix length, and multicast group membership information for all interfaces. And that brings us to the end of Day 5 of Internetworking Influencers CCNA 100-105 ICND1 training course. Don't forget to complete the free practice questions for today's material, which can be found on our website at internetworkinginfluencers.com. The free questions will help highlight the key points that Cisco will expect you to know for the exam. Also, if you enjoy our free training and would like to show your support, please check out our Patreon page. We offer numerous perks to our supporters, ranging from additional practice questions and detailed study notes for each video, to direct access to our instructors to answer any questions you might have. I'll be back next time for Day 6, where I'll cover LAN switching, Ethernet frames, and link errors. I'm Derek Deschamps for Internetworking Influencers. Thanks for watching.